This is section 7.2, volume, the disk method. This is our next big major step into the theme that we started last time, where we take a representative piece of what we're trying to find that's easy to calculate, like the area of the rectangle was, and add up n of those to approximate what we're trying to find. Then take the limit as n approaches infinity and turn that into a definite integral to find something. So this disk method for finding volume is like that, but instead of area, today the topic is about volume. So let's get started with this. The disk method. When you have a region in the plane that's revolved about a line, you'll get a solid of revolution. Let me show you. Well, you have a pretty good picture in your notes, but if this is your axis of revolution and this is the region in the plane that you're revolving around, which is a rectangle, which makes it kind of nice because it makes it doable. When you revolve that around, it creates around that blue line, it creates a solid. So it's like that region, as it passes through space, it leaves solid stuff behind it. And once it goes all the way around the axis of revolution, you have a solid. So that solid that you get will be something that's shaped like this, which of course is a cylinder. We call, in math, in calculus at least, we call this cylinder a disk. That's just the accepted name for it, but it is really just a cylinder. And the volume of that disk is something that can be calculated. So if you'll remember, and this is something that I hope that you remember from earlier work, the volume of a cylinder is the area of the base, which is a circle, so it's pi r squared, times the height. Okay, so the height here, h, is the height of the cylinder, and the radius is that. Now, I will tell you that when you do these revolutions about an axis of revolution, the radius that we get will always be measured from the axis of revolution to the far end of that rectangular piece. So that will be the radius as we go around the axis of revolution. The radius is that. And of course, we've already identified if that happens to be the x-axis that you're revolving around, let's just say it is for just a moment, then that radius is the distance from the x-axis to the curve, and we'll say that the curve is touching it probably somewhere like this, right? Touches one place, makes the top of the rectangle, and that radius distance is going to be, in this case, a value of y, which we will probably think of as f of x. Now, the radius isn't always f of x. I'm just trying to make this clear. This is only if you revolve about the x-axis that would be the case. And we will see examples later on where the radius is not quite that. Related to that, but not that. Then the thickness, or the height of the cylinder, is the width of the rectangle that you're revolving around, which we'll call delta x. Okay, so this height over here is delta x. So using that, if this is the ith rectangle that we're moving around, or revolving around that axis of revolution, and that x value right there is x sub I, so the x we're using for the ith rectangle, as it's revolved around, the volume of this one disk, this one cylinder, if you will be pi times the radius, which for the sake of simplicity, let's assume that we are doing exactly the situation pictured to the left. We're revolving about the x-axis. And so that radius is f of x sub I, because we're getting the y value for that specific x, which takes us to the top of that rectangle, squared times delta x, the height of the cylinder or disk. Then we'll find an approximation of, whoops, almost said area, the approximation of the volume by summing the volumes we get for all of the little disks that we would get, taking representative rectangles that are each revolved about the x-axis, creating a bunch of little disks. And so we'll add up all of these volumes to approximate the entire volume of the region that's being revolved around the x-axis in this case, between x and equals a and x equals b. So I didn't draw that part in there because I was focused on creating the cylinder or the disk. So the volume, therefore, will be attained if we add up infinitely many of those volumes. So we have a limit of a Riemann sum again. I'm just copying down what we have up above. And then we can write an integral because we're taking the limit as n approaches infinity of this Riemann sum, where all of the rectangles start out as equal widths, and that becomes an integral from a to b of pi times f of x is what that becomes in the integral, squared, and then delta x becomes dx. All right, so there's the volume of a solid using the disk method. It's a solid of revolution, so it's attained by doing that revolution. I lost my train of thought, I'm sorry. At any rate, so that's the volume formula, which we obtained by using that simple figure, the cylinder, which we're calling a disk, and revolving around the x-axis produces this formula. So keep in mind that we're revolving about the x-axis for that to be the formula. In a more general sense, we could say that, and by the way, that pi comes out in front since it's a constant, and that's one of the things that I would normally write out in front of the integral. In a more generic way, we're going to have the radius as a function of x being squared times dx. And this will work for any revolution about a horizontal line. And if we revolved about the y-axis and we had a similar situation, so let's say that we're revolving about the y-axis this time, and we have, and this time I'm going to draw a little bit more of what we would see so that you can tell what I'm talking about maybe a little bit better. We're going to have some relation x equals f of y And we're going to go from, let's say, C to D. And we're revolving that region about the line, which is the y-axis, the line x equals 0. So if we draw in a representative rectangle, it looks something like this. That's delta y in width. And when you revolve that around, it would create a disk, a cylinder, that's delta y tall. And the radius, in this case, since we're specifically going around the y-axis, that radius is the distance from the y-axis to the curve is x, which we will represent with f of y. So that radius will be f of y. And the version of this formula where it's a relation x equals f of y and revolving about the y-axis. So this specifically, this situation would be v equals, I'm going to go ahead and pull the pi out like I normally would, pi times the integral from c to d of f of y dy. Okay, that's that specific situation. In a more generalized sense, when we're revolving about any vertical line, it's going to be basically this, where the radius will be some function of y squared dy. All right, so I kind of went off book. They use slightly different letters. They use a capital R for the radius, and they call the width of the disk W, which is more generic than my delta X or delta Y. But those are the two widths that you'll encounter, so that's why I went ahead and went with that. And if you turn to figure 7.14, you can get a good idea of, physically what that approximation looks like. They have one rectangle, and they revolve it around. They show the solid that's created in blue, and that one representative rectangle revolved around is shown there, which creates a representative disk. And then the next picture shows you the sum of 6 such disks. So if you divide it into 6 subintervals of equal width, delta x, that would be what you see. So kind of like a wedding cake or something. If you look at it from, turn it 90 degrees, it kind of looks like a wedding cake. And of course, that is not exactly the solid that's there in blue, but it would be a pretty good approximation. So the volume of that cake-looking thing and the volume of our solid would be pretty close. And of course, with more subdivisions, as n gets bigger and bigger, the cake starts to look more and more like the solid. And of course, when you take it to infinitely many rectangles, infinitely many subdivisions, you get the exact solid. And the integral we've developed, or several of them here, will give you that. So they take you through basically what I said. They use a little bit different notation. They're using a capital R, like I said. That's okay, no big deal. And then they take you through something that I didn't use. It's actually a stronger theorem. I don't know if you did this in Calculus 1 or not, but having infinitely many subdivisions, if they're not equally wide, is chancy. Because let's say that you had a region you were looking at. Let's say it's back to area under this curve from A to B. And we have infinitely many rectangles, but they're not equally wide. And my first one, so we have infinitely many of them, and it's really filling all this in really well until we decide at the very last second to make the very last one really wide. And we'll get that. And the part that's above the curve there, that I'm shading in green, that would be an error. It will not be the exact area. even though I have infinitely many rectangles between A and the left side of that rectangle, if they're not equally wide, that doesn't do it. That doesn't do us any good. And so the partition, the magnitude of the partition is the largest width being used. We also want to claim that that has to go towards 0. We want all widths to become closer and closer to 0. Now, if delta x is always the same width, which you do get if you use b minus a over n, that means they're all equally wide, then having the magnitude of the partition approach 0, that's the same thing as saying let n go to infinity. And so that's why when we're doing this with Riemann sums, I'm making an assumption that we're using equally wide rectangles unless there's a reason not to. And that may be something we talk about at some point, but make them all equally wide, which means every time I do this discussion, it's going to be the limit as n approaches infinity. It's actually also appropriate, and maybe something you're not accustomed to quite yet, but to see instead of saying the limit as n approaches infinity, you'd want this magnitude of the partition to approach 0 of whatever you're taking the limit of. And so, like I said, that is equivalent to n approaching infinity as far as we're concerned, because we're going to use equally wide intervals. So otherwise, again, you're going from the pre-calculus formula, the volume of a disk, which is a cylinder, of course, to the volume of that one rectangle's volume when revolved around the axis of revolution, to having infinitely many of those summed up, which leads us to this definite integral. Okay, so the next page is just kind of a nice summary and nice pictures showing what we were talking about in our discussions. And of course, like I said, the only big difference I see is that they included the width of the partition going towards 0, and they used a capital R instead of a lowercase r. Other than that, no big deal. Okay, so those are two formulas that are very important. We're going to be using that quite a bit to find the volume of a solid of revolution. So let's practice that. It's all nice to get the theory, of course, but it's even better when you actually see how it's used and see an example of how things work and what things look like and what you have to do to get your final answer correct. Okay, so let's take f of x equals the square root of sine of x and revolve that region that's bounded by the x-axis. So think about the sine curve, which goes like this. So it's bound. We're going to find the region that we're revolving is the region between the x-axis and the x values 0 and pi. So basically we're talking about this region right here. Right? So, and we're going to revolve that about the x-axis. So we're going to revolve it about the x-axis. So if we draw in our representative rectangle, it will be delta x in width, and the height is going to be the y value, f of x. I'll say f of x sub I. Which is, of course, the radius of our disk that we're creating. So let me draw that disk. And the radius is f of x. And the height of the cylinder is delta x. And so the volume formula for one of these will be pi r squared, so f of x sub I squared times delta x, the height of the cylinder. So using that volume of a cylinder, volume of a disk formula, leads us to this integral, which we talked about how that happens. So this becomes pi, times the integral from 0 to pi. Those are the upper and lower bounds of the region. So we're going from x equals 0 to x equals pi. Then the function that we're working with is the square root of sine of x. And that will be squared, according to the formula, dx. So, if you square that radical answer, you'll get the radicand, the thing under the radical, and then you can integrate. So we haven't done an antiderivative of a trig function yet, so I do want to review this. The antiderivative of sine of x is negative cosine of x. So if that didn't come straight to your mind, you probably need to go back and review all of your trig derivatives and antiderivatives so that you make sure that you know what this will be. Okay, so there's the antiderivative. Then I want to see the substitution. So that's going to be negative pi cosine of pi minus negative pi cosine of 0. So, and this part here, I don't have to see this, but I'm going to show you what I'm thinking. Cosine of pi is -1, minus the negative is plus, and cosine of 0 is 1. So that becomes 2 pi. And that's our answer. Okay. So once you get the idea of how to set this up and how to identify the radius, that's actually the hardest part. The most challenging part is identifying what represents the radius of revolution and then setting up the integral appropriately. So that's pretty good. Now, the next thing I want to talk about is, well, what if the region is such that, let's see, we're between two things. So between this and this, and we're going from, let's say, A to B. Say that's A, and that's B. And the region we're talking about is bounded above by the green curve, bounded below by the pink curve, and on the left by the vertical x equals A, and on the right by the vertical x equals B. And let's say we're revolving that, still to keep it as simple as possible, I guess. This is a good idea. Let's revolve it about the x-axis. One thing I want to point out that you need to know, which will help us in a future section, like next time I think is when this happens. If your information is given as y is a function of x, that means that you want rectangles that are delta x wide. So that will help you decide here. These would both be functions of x as given, which I didn't say up front. Sorry about that. And since that's the way the information is given, that's what tells me that my rectangle should be drawn. The representative rectangle should be drawn to go delta x wide. Okay? So this time, when that region is revolved about the x-axis, there is space between the x-axis and the pink curve. And so that is that empty space is going to be revolved, and it will create a hole in the middle of the solid. And so when this rectangle is revolved about the x-axis, it doesn't create a cylinder, a disk, it creates something related to that called a washer. Oops, oh, drawing wasn't great. But you've probably seen a washer from the hardware store. Most people have. And you know what I'm talking about, I hope. And the center, the axis of revolution is right where I'm putting that green dot. That's the center of that washer. And the question is, how do we find the volume of the metal that makes up that so that we aren't including that hole in the middle, because only the solid stuff is included in our volume calculation. Well, you need to realize that there are two radii. There's the radius of the inner hole of that. I'm going to call that little r. And there's the radius of the to the outside edge of the washer, which I'm going to call big R, because of course little r is smaller and big R is bigger. Now, I could find the volume of this as if it were solid. That would be pi r squared times h. That would be the volume of the whole thing as if it were solid. I could also find the volume of the hole in the middle, and that would be pi little r squared h. And so the resulting volume for the whole thing is going to be what? What do you think it'll be? The volume of the metal itself. What's going to be the whole thing as if it were solid, that volume of metal, minus the volume of the hole. And so you might notice that pi is a common factor. You might also notice that h is a common factor. So I'm going to factor pi out in the front, and h, I'm going to factor it out to the rear of the expression. And that is how we're going to find the volume of such a solid. And so that's the volume of 1. So I'm going to go back and put a little subscript I. I'm not going to go back and do that to all of them, but that's for 1. And then, so if that's the volume of 1 washer, then we would add up the volumes of all such washers, as we have n subdivisions, n rectangles that are being revolved about the x-axis and creating the washer. And then we make that be forced to be infinitely many n. So take the limit as n approaches infinity, and that would take us to an integral expression. Notice I'm now going a lot faster with these because it's the same idea over and over. So instead of writing all that limit and sigma stuff, I'm just going to go straight to the integral. And we'll have the pi come out in front like we did before. And the outer radius for this is, we never identified that, did we? We should go back and do that. The outer radius is always measured from the far end of the rectangle to the axis of revolution. And if you notice, that is the green curve that's at the top, and that y value from going from the x-axis to that curve is the y value. So big R is f of x. So this will be f of x squared. Then we want to subtract, according to our formula over here, it's big R squared minus little r squared. So let's subtract, and now we need to find an expression for little r. And little r is always measured from the axis of revolution to the close end of the strip. That's little r. So let me say that again because that's really important. the outer radius, big R, is always measured from the axis of revolution to the far end of the rectangle. The inner radius, little r, is always measured from the axis of revolution to the closer end of that representative rectangle. So make sure that you internalize those words, and you might notice that a picture is really, really helpful here so that you can figure out what big R and little r are equal to. So anyway, little r is going from the x-axis to the bottom of the rectangle, which is attached to g of x. And so r is the y value. Since we're going from the x-axis to the curve, it's the y value, which we're going to represent with g of x. Oh, to be consistent, I should have written this over here. And so little r is g of x. So we're going to substitute in little r with g of x as its substitution squared. And then that's multiplied by h. The h here is our delta x. So let me go back and write that in. Our h is the delta x, the width of the original rectangle. And so in the integral, delta x becomes what? Right, dx. And so there's kind of a generic approach to how this is done. When there's space between the region and the axis of revolution, it's going to create a hole in the middle of a washer. And that's how we'll have to address it. So let's see if we can use that information to do an example. Oh, and by the way, there are some nice pictures in there showing you what that looks like. Like figure 7.19 is nice because you can see what the solid looks like. And in figure 7.18, the previous slide, that shows you what one rectangle revolved around, what that looks like. It gives you that washer. And then next slide gives you the formula that we just developed. Let me write it in the generic way they did, because that was kind of specifically f of x and g of x, which may not be the names they use. So more generically, this will be the pi times the integral from a to b of the outer radius, big R, big R of x squared minus the inner radius, little r, of x squared dx. And again, that's the formula for the washer method. And you could get a similar formula if it were a dy situation. Did I ever finish that? No, I didn't. Let me go back up here and finish what I was saying about that. If the information, however, is given in the form x equals f of y, then you're going to want to use a delta y rectangle. And the formula for the volume of a washer given that kind of restriction is going to be very much like the one we just wrote down. The volume equals pi times the integral from c to d. Remember, we use those letters when it's y values, of r of y, where big R is the outer radius, minus little r of y, that's the inner radius, the radius of the hole in the middle of the thing, dy. And so that's an alternate version if it happens to be given so that we are forced to use a delta y kind of setup. All right, now to an example. I said I was going to do that earlier and then got sidetracked wanting to make sure that we talked about the delta y thing as well. All right, let's say that we have two curves. I want to do a fairly decent graph of them. Again, I'm not worried about perfection when I'm graphing. It's basically to give me a good sense of what I'm dealing with. And the picture, to me, really, really helps. At any rate, one of the functions is going to be y equals square root of x. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. So there's y equals square root of x. Okay. And the other graph that we're using is y equals x squared. 0 squared is 0. 1 squared is 1. 2 squared is 4. And draw that part of the parabola. Okay. That's y equals x squared. And the region is that part between them, which I'm going to color in because I'm going to draw this in a different scale so that we can see what's going on better. So sometimes you start with a graph and you go, oh, no, that's not going to help. It's too small for me to draw on and see stuff. So I'm going to expand this. And of course, after doing all of that, we know that the part we're interested in, oh, and I guess we could draw the whole parabola. It's not used because the domain of square root of x is not going to include any negative values of x. But anyway, there's the complete graph of each one. The part I'm interested in is the part that looks like this for y equals x squared. So I'm kind of zooming in on the part I want to focus on. And this being y equals square root of x. There's a nice big picture that we can draw on and see what's going on. Okay, so because of the way the information is given, y equals a function of x for both of them, I'm going to draw my representative rectangle to have a width of delta x. Okay, and my representative rectangle has to go and completely capture for that subdivision of the entire region, for that rectangle. You have to span from one curve to the other. You can't stop short of that. Okay, so we need to find where our axis of revolution is, and it tells us, we've got to read this carefully. We're revolving about the x-axis. And so when that rectangle is revolved about the x-axis, it creates what you might think of as a cylinder, except for this one has a gap between the x-axis and the green curve that's not filled up with solid stuff. So that's going to create a hole. And we're going to need to identify the radius of the inner part. So from the axis of revolution to here is little r, and then big R goes from the axis of revolution, the center of the thing, to the outer edge of the washer. And so we need to find both of those. Well, we're in luck. The axis of revolution being the x-axis means that when we measure the length of big R, it's going to be from the axis of revolution, the x-axis, to the far end of the strip, the rectangular strip. And since we're measuring from the x-axis, that's a value of y. And since it's to the curve y equals square root of x, that big radius is y equals square root of x, or just r equals square root of x. Then the small radius is from the axis of revolution to the close end of the strip of the rectangle. And I don't have room to write it there, so I'm going to write it down here. And that is the y value of our green function, so that would be x squared. Okay, so let's set up our integral, because once you've done all this thinking visually and what's going on, all you have to do basically is make sure you know the formula, and you can substitute into it quite well. So v will equal pi times the integral from, I didn't find where they intersected. Well, actually I did. When I graphed this over here, I knew that they both went through 0, 0, and 1, 1. But again, if you didn't know that just by having graphed it, you would want to set those equal to each other and solve for where they intersect. So if I squared both sides, that would be x to the 4th on the left equals x on the right. Get that polynomial to be equal to 0. Then factor, there's a common factor of x, leaving x cubed minus 1. And the x cubed minus 1 factors to be x minus 1 times x squared plus x plus 1. And if someone needs for me to talk about how I factored that difference of 2 cubes, take note of this and make sure you ask me about it in class. I'm thinking maybe some of you know it. So if this factorization leads me to something that's equal to 0, this product equals 0, that means one of the factors is 0. So if the first factor is 0, that means x is 0. If the second factor is 0, that means x is 1, which we got from graphing. And this last one, to solve that, you'd use the quadratic formula, opposite of b plus or minus the square root of b squared, which is 1, minus 4 times a, which is 1, times c, which is 1. So 1 minus 4, all over 2 times 1, 2a. And that's going to lead me to non-real solutions, which I can't use in this setting. We're going to be dealing with real numbers for the most part in this course. So these non-real answers just don't have an impact. So the region, of course, we now found, and we've shown how we got that. It will go from 0 to 1. We'll take big R, which is square root of x squared, minus little r, which is x squared, squared, dx. And although we did a polynomial antiderivative earlier, I want to go ahead and finish this one. So let's simplify first, which is always a good idea when you're trying to integrate, is do any simplifications inside you can. Square root of x squared is x, minus x squared squared is x to the 4th, because you multiply the exponents. Okay, now this should, once you get that far, should be easy. The antiderivative of x is x squared over 2, which I'm going to call 1/2 x squared. Antiderivative of x to the 4th is x to the 5th over 5, which I'll call 1/5 x to the 5th. Evaluated from 0 to 1. Then I'm going to start by substituting in 1. The upper bound goes first. Minus, now substitute in to that formula 0 for each x. And as it turns out, the back end of this is 0. So it just kind of disappears, but I wanted to show you that so that you get an idea of how that works. And so this ends up being 3 pi over 10 when you do the arithmetic. And again, if there's any algebraic or arithmetic thing that I do that you don't exactly remember or don't understand, because I'm skipping a step from something that's supposed to be easy for you from a prior course, please ask in class, because I don't want you to wonder how things came out to be what I said. If you don't know, you don't know. So please ask. All right. So find the volume, example 3, find the volume of the solid generated when the region between y equals x squared minus 8x and y equals 8x minus x squared, oops, like that, 8x minus x squared, is revolved about the line y equals negative 20. Okay, so this is where you're going to have to really think about what's going on so that your big R and little r are the correct numbers. So we're going to draw a really good picture and then set up the integral. So let's worry about graphing these first. And this would be of the level of difficulty that I would expect that you could graph this without any kind of technology at your fingertips. So let me teach you how I would graph this. First of all, I know it's a parabola because it's quadratic. And the leading coefficient is positive 1, so I know it'll be a parabola opening upward. I also know that I can factor out a common factor of x. And if I were to set that equal to 0, that will find me my x-intercepts of this graph. And so the x-intercepts are 0 and 8. So let's say 8 is about right there. And of course 0 is at the y-axis. So I'm going to have a parabola that has an x-intercept of 0, an x-intercept of 8, and it opens upward. And of course, because of symmetry, the vertex has to be halfway between 0 and 8. So at 4 is the vertex, and it is wherever it is. Okay, doesn't really matter that I find that out. You know how to do that from your college algebra days, I'm sure. The x-coordinate of the vertex of a parabola is, the x-coordinate is x equals negative b over 2a. If you had to find that, you could find it. And then you could substitute that into the equation and find out what the y-coordinate is. To be quite honest, I really don't care, because it's not going to make a bit of difference to me, I don't think. Well, actually, I'm going to take that back. You won't have this happen, but if that line that we're revolving about went through the region that we're going to get, we'd be in trouble. We're not going to talk about that. That's not going to happen. So not to worry, it won't be a deal. And I'll point that again. I'll point that out again when we get to it, because I want you to understand what I just said. Okay, so the other one is also parabola, but the negative in front of x squared means it opens downward. And I can factor the x out of that one. This should sound really familiar. And set that equal to 0 to find its x-intercepts. And of course, they're the same as that one. So I'm going to call this one y sub 2. And it has the same x-intercepts, but it opens downward. And it'll look something like this. All right, so the line y equals negative 20 is down here someplace, and this does not have to be to scale for this to work for you, so don't let that bother you if it's not perfectly to scale, because you're looking for ideas of how to set things up, not for a perfect drawing. Okay, that's your axis of revolution right there. And like I said, that axis of revolution won't go through the figure. Just be aware of that. Okay, since these are both y equals a function of x, we want delta x rectangles, so I'm going to draw one in right here. Doesn't matter where I draw it in, just somewhere. And that, of course, is delta x wide. Notice the space between the pink curve and the red line. That means that this is a washer when we draw it out, so we're going to have a washer because of that empty space between the pink curve and the axis of revolution. And the height of that will be delta x. And of course, our task is to find an expression for big R and little r. So Big R will go from the axis of revolution to the far end of the rectangle, which in our picture is from the far end of the rectangle to the axis of revolution. That's big R right there. Okay, it's supposed to have been R right there. All right. So what is that? Well, again, and I did this in an earlier video. When you are trying to figure out an expression for something, like here we're trying to find out, well, what is big R? You might want to use some numbers as examples to get your thinking straight. So let's say that I think of that number at the top of that rectangle. Let's just pretend like it's 3. I have no idea if that's beyond the top of this parabola or not. I'm just making up a number. And I want to know how far is it from 3 down to negative 20. Well, I think you'll agree that it's 23, right? How would I get that with the numbers 3 and negative 20? Well, if you think about it, isn't that 3 minus negative 20? Doesn't that work? And so, in a more generic sense, that big R value will be like 3. That was the y-coordinate on the green curve, which is our y sub 2 value. And then minus negative 20 becomes plus 20. And so that's what our big R is. Come back over here and write that here. Big R, we just discovered, is y sub 2. Make sure you pick up the correct one. 8x minus x squared. Y sub 2 plus 20. All right. Now, let's look for little r. Little r is the distance from the axis of revolution, the center of the cylinder, to the close end of the strip. And that means we're measuring from the axis of revolution to the bottom of that rectangle to get little r. And again, if you need to work with example numbers, please feel free. If you don't know what that expression is going to be without this, please think about this. So let's say that the bottom of that rectangle is at negative 2. How far is it from negative 2 to negative 20? Well, I hope he said 18. So we would get 18 by doing what with the numbers given, negative 2 and negative 20? Isn't that the same thing as negative 2 minus negative 20? Hopefully that sounds familiar. Isn't that true? Yeah, that's right. So that means that little r, in a more generic way, is going to be where the negative 2 is. That was the y value of the pink curve. So that's y sub 1. Whoops. No, I guess that's all right. Y sub 1 minus negative 20 is plus 20. So look at the parallel nature of those two expressions. Little r is y sub 1. And again, make sure you pick up the correct version of that. X squared minus 8x plus 20. Finding these two expressions, the expression for capital R and the expression for lowercase r, is the most challenging part of these problems, because once you have that, it's a formula. It's really just a formula. Now, since they have the same x-intercepts, that means that's where where the region that's being revolved starts and ends. So the volume will be pi times the integral from 0 to 8. Those are the two x-intercepts, which defines the region, is everything between those two, of big R, which is negative x squared plus 8x plus 20 squared minus little r squared. So that's little r is x squared minus 8x plus 20. Quantity squared times dx. Now, I would like for you to realize that this type question is probably one, because of the complicated nature of what we just did, one where I would say set up an integral to find the volume and then use your calculator to approximate it. Even though that said, it wasn't what I just said, that's not what the example asks you to do. So for practice, I would like for you to simplify, do the squaring and do the squaring and then do the subtraction and the substitution of into 8n for x minus the substitution of 0n for x. And I'd like for you to see if you can get this correct answer, 20,480 pi. And for your arithmetic, I fully expect you to use a calculator, of course, over 3. And then also, because this is a really complicated expression, see if you can type this using that math 9, the FNINT, the function's numerical integral, and see if you can find the approximate answer using your calculator. And that should be 21,446.606. And so these are answers that you can verify using Calculus 1 techniques of integrating and substituting and subtracting, all that, to see if you can get this first answer, and then typing the integral expression into your calculator to see if you can get this answer. And if you can do all of that correctly, you can handle any problem I throw your way. Because this is one of the most complicated ones that I would have you do the Calculus 1 part on and get that exact answer. And usually if it starts getting pretty complicated, that's when I'll say just set it up and then give me the answer as a decimal approximation using your calculator. All right, so on the next slide, I acknowledge that so far the axis of revolution has been horizontal for all the examples we've done. We're going about the x-axis, and then this one about the y equals -20 line. In this next example, we're going to have an axis of revolution that is vertical, and in that case we'll integrate with respect to y. All right, and that's going to take us to two separate integrals. I do want to talk about why that happens and show you a level of complication that we kind of hope doesn't happen very often. Anyway, the graphs that bound the region that will be revolved are y equals x squared plus 1 is one of the boundaries of the region. Y equals 0, the x-axis, is another boundary of the region. X equals 0, a vertical line that goes through the y-axis, or is the y-axis, and a vertical line x equals 1. Those are the boundaries for this curve. And revolving this about the y-axis. So let's start with a view of what this function looks like. Or, I'm sorry, the region, what the region looks like that we're revolving. Y equals x squared plus 1 is a parabola that opens upward with its vertex at 1. And it's only that half of it I need. I mean, I could sketch in the other half if you want me to. But as it turns out, the right-hand side, that's all we really care about. That's one boundary. The other boundaries are y equals 0, the x-axis, x equals 0, the y-axis, and x equals 1, which is right there. So that's what our region looks like. Now, one thing I haven't mentioned yet, which is really important, is even though this is written y equals x squared plus 1, and I told you earlier that typically we'd want to use delta x in that situation. But we don't know the technique yet that you could do delta x with, and actually the other technique is way easier than this one, and we'll see this same example in a later section. I think it's the next section, in fact, where we do this same problem but use delta x and we go, wow, that's so much easier than what I'm about to talk about. The reason you want to use delta x as this problem is way better. But we were told to use delta y, so that's what we're going to do. One of the reasons this is not a good call is that if you draw a representative rectangle, it could go from one vertical to the other. And if that were the case for the whole thing, we're good. We're done. I want you to look up here at some of these other pictures. The representative rectangle will go from the pink to the green. Anywhere I drew that, that would be true. Let's go up further. In this one, the red rectangle goes from the green to the pink. And anywhere I drew a delta x rectangle, that's what it would do. Okay, so that's the idea, is you want it to be the same idea the whole time. Otherwise, it makes it way more complicated. And in this particular case, the upper part of this figure, if I draw a representative rectangle right here, it goes from the curve to the vertical, which is a different situation. And so what we have to do is we have to separate this into two parts. We're going to be going from vertical to vertical, from the x-axis up to this line. And then when we get past that line, we're going to go from curve to vertical. And so that distinction is really important to make, that we have two different things going on. Let me indicate, of course, that this was at 1, and that's important. And these are delta y rectangles, as we were told to use. And so consequently, we're going to have two sets of things. We are revolving about the y-axis. And so let's work with the bottom one first. That does not have space between the figure and the axis of revolution. The rectangle touches the axis of revolution from 0 up to 1. So this is, for the first part, the bottom part, that is a disk, not a washer. It's delta y, and all we have to do, delta y tall, and all we have to do is find out what the radius of that is. And of course the radius, no matter where you draw that, the radius, the distance from the axis of revolution to the far end of the strip, is always constantly 1. So r here is constantly 1. And so the volume of the region, which is actually a square, revolved about the y-axis, could be gotten by following the steps of the process, pi times the integral from y equals 0 up to y equals 1 of r squared, where r is always 1, times delta y becomes dy. And that's the first part. So that gets us all of this. Okay, that's what that does. Now, for the part from 1 up to, I guess we need to find out where that is. See, that's going to be when x is 1 on the pink curve. So f of 1 for the pink curve is 1 squared plus 1 is 2. So that's going to be a y value of 2. So from 1 to 2, we're going to have a rectangle that goes on the left from the curve over to the right, the vertical line. And so since there is space, empty space, between the rectangle and the axis of revolution for this, when we do this one, it's going to be a washer. Which is delta y tall. The inner radius is the distance from the axis of revolution to the closer end of the rectangle. And since we're measuring from the y-axis to the curve, that's a measure of x. So that little radius is x. But since we're doing a dy problem, we do not want that to be a function of x. We want that radius to be a function of y. So that means we're going to have to take the equation y equals x squared plus 1 and we're going to have to solve it for x. This is another reason why you don't want to do this problem this way. I'm showing you the worst way possible first so that you can maybe understand why the other way is so much better. We'll get to that in the next section. So solving for x, we would get x equals plus or minus the square root of y minus 1. And of course, we're dealing with the positive x's for this half of the parabola that's actually being used. So we would want to make sure that we keep the positive version of that. So that means that our r, which was x, is now known to be, this is little r by the way, now known to be the square root of y minus 1, that function of y. Big R, the distance from the axis of revolution, the center of this washer, out to the outer edge of it, big R, is always measured to be the distance from the axis of revolution to the far end of the strip, which, since that's a vertical line, that distance we're moving is x equals 1, so the radius is the big radius is always 1. And so our integral for this one is, I'll call this V2. I'm going to go back and call this V1 because we have two different regions, so we have to, in the end, add these two things. So this is pi times the integral from, this part of the region goes from y equals 1 to y equals 2 of big R squared minus little r squared dy. Okay. So again, this is a good one for you to practice and make sure that you can get correct answers on your own. This red one ends up being pi. So that'd be something you could test yourself on, make sure you can do that. And the second one ends up being pi over 2. Again, check that one, make sure you've got your Calculus 1 skills in order. And so the total volume of this region, which is V1 plus V2, is equal to pi plus pi over 2, which is 3 pi over 2. Now the thing I have written above in red, that volume using an integral, actually that was kind of silly of me because that was really a square region that was being revolved. That's just creating a great big cylinder whose height is 1 and whose radius is 1. And so we could have just used the pre-calculus formula that that's pi times r squared times the height 1. So yeah, sometimes we'll end up seeing, oh my gosh, that was just a simple cylinder. I could have done that using pre-calculus, but I feel good that I got the right answer using calculus. Anyway, even if I didn't see that, the calculus approach would give me the right answer. All right, I'm going to stop this recording and continue with the next idea in another recording. So go ahead and move to that one after you've listened to this one.